Hey friends, week 3 in 7313, and once again a little bit of a review from 7311. Hopefully it's a review because I imagine you had a really good professor for 7311, so you probably know this like the back of your hand. But for what it's worth, we'll go over it again, just to make sure we have terminology and everything straight. So this week we're looking at correlation and regression, and really the big distinction between them. So this first lecture is going to focus on correlation and make sure we're all on the same page and work out some of the nuances of it. And then the next one we'll deal with what regression is and how it differs from correlation. So obviously, gospel for research should always be correlation does not mean causation, right? And I'm sure you guys know this because you're brilliant and yeah, but it's something I can't emphasize enough because the real distinction between correlation and regression in many ways is the question of causation, and we'll talk more about that. But correlation just simply means that two variables move in statistical accordance with each other, right? So this chapter, and I pulled this from a different text, so this is something you don't actually have in your textbook, but I think is a really good way to look at it. It's called Ice Cream and Crime, and as you might know, there's an extraordinarily strong correlation and significant correlation between ice cream sales and violent crime, right? And so of course many people might say, oh well, it's obvious. Somebody gets brain freeze and next thing you know they're busting a cap. Or, someone celebrates a violent crime by having an ice cream sundae. Right? And you can just see the headlines too. I can just see it now. Some news agency will see this and be like, you know what? Ice cream is clearly the tool of the devil. We got to ban all ice cream, got to ban Bluebell, God forbid, and because it's causing people to be violent. This country would be far less violent if we didn't eat so much ice cream. And I'm being facetious, but people would run with it. And there would be protesters out there, life, not ice cream, and all these signs too, and it would just... the fundamentalists would get behind it too. It would be, oh, well, you know what? Ben & Jerry's is one of the biggest ice cream sellers in this country, and one of them is homosexual. So maybe ice cream's linked to homosexuality, and then it just runs. None of that is true. I'm being very facetious. But there's a third variable at work here in correlation, right? If you think of why ice cream sales would go up when gun crime also goes up or violent crime goes up, there's a third variable. And if you haven't already guessed it, it is temperature. When it is hotter, of course, you are more inclined to eat more ice cream. When it's hotter, you also get more aggressive. And, if you don't believe me, stand outside for a few minutes and then think of something that makes you upset. Or stand outside for a few minutes and read an email that your colleague has sent you that's really made you angry. Right? The fact of the matter is people are more aggressive and ultimately violent when they are hotter. Police departments know this. Actually, if you take any major police department, New York, LA, whatever, they will schedule more cops on the beat when there is a higher than normal temperature. Right? That's just the way it is. And so what we're seeing here is not a causation. Ice cream and gun crime or violent crime do not share a causational relationship, simply the fact that they move in a pattern that is predictable based on their relation to temperature. Right? So that's what I want to kind of establish here. We'll talk more about it as well, but that's a good nuanced example of why we cannot infer causation with correlation. So some indicators, once again, this should be a review. We've talked about the correlation coefficient, little definition there, a numerical relationship that index that reflects relationship between variables, right? That's all it is. Doesn't establish causation, doesn't establish prediction. And this is represented by a lowercase r italicized, right? Hopefully that sounds familiar. We saw it this past summer. Obviously, it's given as a value between -1 and 1. You cannot really achieve -1 or 1. They're kind of more theoretical constructs, so it would be exceptional for two variables to be perfectly correlated. That's what it's called, perfect correlation, when it's a 1 or a -1. So just kind of keep that in mind as well. Anyway, obviously a negative correlation, a negative R value indicates an inverse, indirect, or negative correlation. And this is something I didn't go into a lot of detail with in the previous course. Inverse, indirect, and negative all mean the same thing, right? And I think in the class we used negative a lot when we were talking about this. I would prefer, and I think it sounds a lot more professional, if you use the term indirect. And I've got a really good reason for this. I'll talk about it in just a moment. But indirect, I think, is the preferable term for this kind of correlation. As I said, all three are synonymous, but indirect is going to sound better, and we'll talk about for why in just a moment. A positive value, of course, a positive R value indicates a direct or positive correlation. Once again, in the previous course we talked about it in terms of positive. I would actually prefer you talk about it in terms of direct. And as I said, there's a reason for this, not just my personal ego, but a really good reason why you might want to do it that way. So kind of keep that in mind as we move forward as well. And obviously, as you learned in 7311, the further it is from 0, the stronger the correlation. Between 0 and 0.3 is kind of weak. Between 0.3 and 0.5 is moderate. And anything above a 0.5 is going to be considered fairly strong. As I said in the previous course, this isn't really gospel. This is kind of a general rule that I've got for my course. But those are kind of the increments that you can use to judge by. And of course, this works in the inverse as well. Notice it says the further from 0, and that can be negative or positive. It doesn't matter. As it moves away from 0, the correlation is stronger. Just as I said, keep this in mind. I feel like I'm saying that a lot. Anyway, whatever. If you can hear my stomach rumbling in the background, by the way, I'm sorry. I'm really hungry. So the other indicator that we've talked about in correlation is going to be the Pearsons Coefficient. This is the significance. And as the definition indicates here, a measure of the probability that the relationship between the variables is strictly chance. Keeping in mind in statistics, we don't deal in chance. We don't want risk. We don't want uncertainty. We want to be as certain as possible. That's why we even run the statistics. So we want our p-value, as we talked about last time, or last course, to be as low as possible. Obviously, it's given as a value between 0.000 and 1. And I made this distinction in the previous course, but I want to draw your attention to it again. Notice I didn't put 0 and 1. The fact of the matter is you can never be 100% certain about your analysis, right? So on the slide there where it says 0.000, I'm not actually referring to 0. I'm not saying there's a 0% chance that the relationship was just incidental, right? Or coincidental, rather. Okay? What I'm saying is there is not a 1 in 1,000 chance that it is. So you notice that it's 0.000. There is a 1 somewhere after those zeros, but it's not in the first 3 decimal places. So what you're saying is not that there's 0 chance, but there's less than a 1 in 1,000 chance. Okay? So you're showing a great deal of confidence in the data that you've got. Obviously, the higher the value, the more likely the relationship is by chance, and we don't want that. As I said, we have to really fight our instinct and be like, oh, we want the value to be as high as possible, to be as large as possible. This is America. Yes, I understand we usually prefer more substantial things, a higher value in most things, but no, of course, we want to keep it as low as possible. And the level of significance, I didn't really mention this much in 7311, but it's somewhat subjective. It varies. I wanted you to think that it was set in stone because for our fields, for research and education as well as psychology, it is set pretty much in stone at the old faithful 0.05, right? But that is not across all fields. And as I said, I didn't cross that bridge then because I didn't want to cause any confusion. Some other fields use much more rigorous p-values. If you're following the vaccine research that's going on for COVID, for example, they would use a p-value that would probably have maybe 7 zeros after the decimal place before you see a 1. So we're talking about a substantially, incredibly more rigorous statistical threshold. And obviously, the reason for that is, if you and I are calculating star scores, there's some risk in the statistical analysis we're running. If you're trying to save potentially thousands and thousands of lives by developing a vaccine, of course, you need to be much more precise. So their level of significance is extraordinarily more stringent than ours. You see this too in most types of things. I'm a geek, so I know like when they're doing research for rocket launches and things like this, detection of stars and planets, their p-values are incredibly more rigorous. So anyway, 0.05 is kind of a fairly low bar. But what it does mean for us is that we are 95%, at least 95% confident in the results we found being accurate. So it's a good place to be. So direct correlations. We'll come back to direct correlations. Notice I'm referring to it as direct. It would be lovely if you could get in the habit of calling it direct rather than positive. I have to think it through. I don't even think of it in that context. So obviously when x increases, y increases. Let me caution you, I'm simply using x and y as just variables, not causational. A lot of times we'll talk about how x predicts y, or x is the independent variable and y is the dependent. Kind of forget that mindset for the moment, right? And obviously the more time you spend studying, the higher your exam score will be, right? So as x goes up, time spent studying, y goes up, your exam score, right? And I know what you're thinking. You're thinking, well, there's been times where I've taken an exam that I didn't study for at all and I crushed it. I got an A, right? First of all, you should never tell anybody that. Least of all professors, because it's like a personal insult when you tell a professor that. But also because these are not gospel. These are not hard and fast relationships. Relationships rather. They're more trends. If you think of correlation as more of a trend, right? Any professor will tell you if you spend more time studying, your grade should improve, right? But that's not certain. That is not certain. I took tests when I was a undergrad or a grad student where I studied my butt off and still got a lower grade than I thought I would, right? So you understand, these are not set in stone. These are simply trends. In this case, when x decreases, y increases. When x decreases, y also decreases. So the less money you put in the bank, the less interest you will earn. Obviously, that makes sense because there's less principal for you to earn interest on, right? This is why I want to point out that we don't use the term positive. If you look at this second example, when x decreases, y decreases, right? Because they're both decreasing, you might be inclined to call that a negative correlation, right? No, this is still a direct correlation because they are both moving in the same direction, right? This is why I want you to use that particular label. It would be easy to look at the first example and say, oh, that's positive, and look at the second example and say, oh, that's negative. This is why I don't like the confusion of terms and choose to go with the direct rather than the positive as a label. If you look at a scatter plot, here's a good example of it here, right? So in this case, our y variable is weight, our x variable is height. Obviously, as you get taller, you probably tend to weigh more, but this isn't always the case. You have quite tall people who don't weigh very much, and quite short people who do, and everybody in between, just as God made them, right? So there is, of course, a trend that height will not predict, but height is related to weight, but it's not, once again, a very... It's a correlation rather than causation. So just because you know someone's height doesn't mean you can predict their weight to a great deal of accuracy, and vice versa. So what I want you to note, though, for the scatter plot is the line of best fit, for all of you math teachers out there, or former math teachers anyway, the line of best fit is pointing up and to the right. You'll see this on all direct correlations. So as x increases, y increases, and vice versa. As I said, no causation, so we don't have to establish it in a certain direction. Right? So indirect correlation, actually, I'm going to stop this one here, and I'll start the next video right here. Let me jump in here.